first talk of the day is MR acquisition and preprocessing to optimize surface analysis. And this is by Dr. Matthew Glaser. So can we please give a round of applause for Matt?
So we will see if these polls work. So we can leave that up there for a second. So I'm going to talk about what you need to do if you want to do a surface-based study to sort of optimize your MRI acquisition and a little bit about preprocessing. And I guess we're going to use the laser pointer since the mouse doesn't actually show up on the screen. Okay. So I have a few disclosures. So what is surface-based analysis is a first question. Oh, that's interesting. So I don't think the polls are going to work even live here, unfortunately. So if people want to give a show of hands, what is a surface-based analysis? There are three options here. So first option, if you display results derived after smoothing and averaging in the volume on a surface mesh, is that what we're talking about with the surface-based analysis? Show of hands of whether or not that's what we're talking about. The second option is aligning cortex across individuals on the surface, and if doing smoothing, to do it on a surface mesh. So that's actually what we're talking about here in terms of surface-based analysis. Surface-based analysis, I would have been curious to know if people had done it before, or most people in the room were new to this. Different surface-based file formats. GIFTY is the first standardized surface-based file format used across multiple software platforms. NIFTY is a volume-based format, as folks know, and SIFTY is a way of getting both surface and volume into the same file. Various things improve with surface-based analysis over volume-based analysis. Spatial localization precision is one of the biggest ones. Statistical significance of results will improve with a surface-based analysis. It's easier to visualize cortical signals. It's easier to interpret them when you're looking at them on the surface. But oftentimes, surface-based analyses take a bit longer because you have to reconstruct the surface meshes and segment the brain. But then downstream steps actually can be faster. Okay, so why should we bother with a surface-based analysis? Why attend this course? We've been making blobs in the brain and 3D M&I coordinates for around 30 years. This is an interesting clinical application of surface-based analysis that I wanted to share with you guys here. So we have a patient who has Lou Gehrig's disease, or ALS, and is no longer able to speak. And has enrolled in a clinical trial to try to have a brain-computer interface that will enable them to speak basically just by thinking. But one of the really critical factors of success here is putting the recording grid, what's called a Utah array, which is an 8x8 or 64-channel array, and you can see, whoops. You can see 4 of them here. That's an interoperative photo. Where are we going to put that array in the brain to actually be able to record what the person is thinking? And so what was done in this particular study was to map the HCP's multimodal parcellation onto this particular patient's brain. To do that, first we acquired MRI scans that are along the lines of what I'm going to talk to you about in a moment, but what we call an HCP-style MRI acquisition with high spatial and temporal resolution fMRI and T1 and T2 weighted imaging. And so we've gotten the the group average areas onto this individual's folding pattern. So here's area 44 we think of as Broca's area, and area 6V is more think of as a a premotor area. And then these are probabilistic maps of basically showing the variability in those cortical areas with the particular surface registration algorithm we use to get this onto this individual. And then here we have functional networks. So this is the language network. We've got Broca's area here and Wernicke's area here. This is the group average network mapped onto the individual, and this is the individual's own network here. And so we put 4 grids on this patient. 2 are in area 44, what we would think of as Broca's area, the place you would expect to be able to record speech from, but also 2 in the premotor cortex. And that was based on some prior work that was suggesting that maybe the premotor cortex was useful. It turned out that this particular grid location right here, so we see that it's in the language network, but it's in the premotor area 6V, actually enabled very accurate decoding of speech. If I remember correctly, for this study, there's another one that actually is about to come out that was even better than this one. But if I remember correctly, it was about maybe a 5 or 10% error rate for a small vocabulary of 50 words, and it was the first demonstration of accurate decoding of 125,000 words, which is like more words than most of us in this room know, so basically a complete vocabulary. And that was an error rate around 20%. So basically, just by putting a grid in this one location here, in this patient, the computer was able to talk for them just by them thinking the words that they wanted to say. And so this was published last year, and we have another one coming out soon that was even better than this one. So, you know, this little hotspot here, it's one part of one cortical area that happens to be part of the language network, was really important for being able to solve a clinical problem. So data from the sheet-like cerebral cortex is more easily analyzed and visualized on surface models. This idea sort of first got its start in around 1980 when David Van Essen and his student John Mansell were working on it. And by the time fMRI was invented, computers could actually help us make surface models. So the initial, this initial thing in the 1980s was a pen and paper drawing, but by the time fMRI came around, we could start projecting fMRI into the surface. And this is a classic study by Marty Serino in 1995, where he's done, what we would consider to be relatively primitive fMRI at this time. They didn't have 3 Tesla back then. The voxel size was bigger than I'm about to recommend. But they got the fMRI data onto the surface, and we're able to see, visuotopic maps. So basically, fovea versus periphery, that's our eccentricity map here, or polar angle, whether you're sort of in the center of the field of vision going up and down. This is the vertical meridian, or the horizontal meridian kind of goes like this. And so that's what we're displaying here, basically where in visual space one is. And we could map this on the cortical surface. We could find visual areas like V1, V2, and V3 based on these maps. And studies of the visual system have largely followed Marty Serino's lead, analyzing data on cortical surfaces, and we've learned an enormous amount about the visual system in humans by doing this. It's helped a lot, but many other parts of the brain, particularly in cognitive regions, haven't had this level of attention. Most of the studies have been done in volumes and sort of, these blobs that are hard to put back onto actual cortical areas have been generated, or MNI coordinates. So there's a lot of cool stuff that remains to be discovered by applying surface-based analysis to the brain. A lot thought, I think, that's been missed by some of the volume-based studies, like that little hotspot that I showed you in the last slide. Okay, so 2 topics today. How to optimize the data acquisition of a new MRI study for surface-based analysis, including if you're wanting to get into surface-based analysis, but you have data that was acquired before you thought about that. What are the limitations and what can you still do? And then a little bit about surface-based processing pipelines and their benefits for spatial localization. So first, the acquisition side. So this is a simple point, but I'll make it anyway. You really want to have isotropic resolution. And most research studies these days are doing this, but if you're wanting to use data from, say, a clinical study, often clinical scans are not isotropic resolution. So I know we have some future neuroradiologists in the audience, and he's going to quickly realize when he gets into this field how primitive many of our clinical acquisitions are. So this over here is a typical T2 weighted image, and we can see it has nice resolution in the axial plane, but looks like crap in the sagittal plane, whereas we really want isotropic resolution. Another key thing, if you're trying to optimize MRI protocols, keep this in mind that a lot of the protocols that come out of the default tree will be upsampling the images to isotropic, and they'll actually be blurrier along one axis or another. In the research world, I've seen a lot less of that than I have in the clinical world. But you want these 3D isotropic acquisitions. We have them for T1, T2, FLAIR, SWI. There are efficient sequences for this. Vendor acceleration methods are making these faster. In the research side, we have within sequence motion correction. That's very helpful because some of these scans can still be on the order of 4, 5, 6, 7, 8 minutes, depending on what resolution you try to get. And it really helps to be able to correct for any within scan motion. Unfortunately, we don't have that clinically for somewhat unclear reasons, but we've used it on thousands of subjects in the HCP, and it's been very helpful. Then for diffusion, perfusion, fMRI, these are all based on 2D EPI acquisitions, so we want equal slice thickness and in-plane resolution, and we don't want any gaps. And things like simultaneous multi-slice imaging make these techniques a lot faster, a lot easier to achieve those isotropic resolutions with reasonable scan times. So another important thing that we want to consider when designing an MRI study for a surface-based analysis is we want to consider the neuroanatomy that we're studying, and the cerebral cortex is a big part of that. So this is a group average map of cortical thickness here. And this is the histogram of that map showing basically which cortical thicknesses are more or less common. So the mean cortical thickness, the most common cortical thickness is around 2.6 millimeters. And the minimum cortical thickness is around 1.6 millimeters, kind of in visual or somatosensory cortex. So historically, most fMRI was acquired with larger voxels than our mean cortical thickness here, sort of in this range from 3 to 4 millimeters. But with the HCP, one of the things we really tried to do was push the spatial resolution a bit higher so that we were getting less than the mean cortical thickness. So for a clinical study, ideally you want to be less than 2.6 millimeters. 2.4 is actually a sweet spot. That's not quite as fine as we did for HCP, but oftentimes people cannot afford many hours of scan time like we had for the HCP. So 2.4 is taking a little bit of a step back to gain some SNR, but still being less than that 2.6 mean cortical thickness. And then for your structural imaging, your T1, your T2, your FLAIR, ideally you want it to be 0.8 millimeter isotropic or less, which is half the minimum cortical thickness, and that helps make sure you have at least 2 voxels, even in the thinnest heavily myelinated cortex, like in the visual cortex or the somatosensory cortex. So what if your fMRI resolution is too low? Well, this is a map showing basically how much mixing you have across cortical folds from partial voluming, and you can see you have quite a bit of mixing with 4 millimeter data. 3 millimeter data, it gets better. 2.5, it's quite a bit less, and 2 is basically gone. So it can be difficult to tell if an activation is on one side or the other of a fold, and one side or the other of a fold may be very different. You have, on the central sulcus, for example, you have sensory cortex on one side and motor cortex on the other. And as I'll show in a little bit, smoothing can also cause, in 3D, can also move activations around, and I'll say more about that in a moment. So to optimize structural MRI, like I said, the one number to keep in mind is 0.8 isotropic or better if you can do it. Within scan, motion navigators are helpful in making a higher proportion of your scans successful. And it's a big problem in clinical neuroradiology as well. I'd love to see the vendors implement this for, they're all interested in deep learning now, but have some motion correction would be helpful. Contrast parameters are also things to consider here. So if you want to have an easy job segmenting the brain into CSF and gray matter and white matter, you want to have your tissue peaks to be roughly equidistant from each other. So we see our gray matter is about halfway between our CSF and our white matter, and for our MP range, these parameters do a nice job of getting you there. T2 or flare, you use a variable flip angle, and here our CSF's a little further away in this particular example. And then, as I said before, you got to check that the vendors aren't fooling you. They like to say, we're going to acquire the resolution at 0.8 isotropic, but really in the slice plane, they're getting it at 1.4 or something like that. So you have to make sure you're actually getting full resolution. Compressed sensing and other parallel imaging techniques can be very helpful when used in moderation. So another important thing to keep in mind when you're doing a surface-based analysis that's perhaps it's a good idea in a volume-based analysis too, but it's more important in a surface-based analysis is dealing with image distortion. So EPI images that you use for fMRI or diffusion or perfusion have more distortion in them and different distortion than in your structural images. And basically, it's air near the brain tissue and the sinuses or mastoids that cause those distortions. And here I've basically mapped the amount of distortion in different brain regions in terms of cortical thickness. So our red areas here are more distortion than a mean cortical thickness. And that means if you try to map the data from the volume onto the surface, you're going to miss. You're basically going to you're mapping non-gray matter signal if you try to map the data within the cortical ribbon. The green areas are half a cortical thickness, so you'll miss by half. So if you don't correct for distortion, you'll do okay in these blue areas. There's not so much distortion, but you're not going to be able to get the signal accurately in the red areas, and you're going to be compromised in the green areas. But you can correct for this distortion. In the past it hasn't, but it's becoming much more common now in brain imaging research. Clinical practice is still lagging behind, unfortunately, though. Things like parallel imaging, within plane parallel imaging like IPAD or GRAPPA or SENSE can help. Segmented EPI can also help, although it makes scans longer. You need some measure of the magnetic field. It can be a vendor standard field map that uses 2 different gradient echoes and a phase difference image, or it can be 2 different spin echo images with reverse phase encoding directions. Either is good for measuring magnetic field. Also, you're going to still have the issues with signal loss, fMRI, susceptibility, perfusion, all use gradient echo images, and they have signal loss. It's in the same areas as the distortion. This is basically a proportion of subjects that have severe signal loss in different places, so we can see orbital frontal cortex, inferior temporal cortex. They're going to be black holes, even with the surface-based approach, but they were black holes in a volume-based approach too, so this is not a new thing. And there's no way to correct for this. Once the signal is lost, it's lost. Doesn't affect spin echo images, though. So very briefly, a point about imaging fast for fMRI TR of around 1 second is really helpful to remove artifacts and noise from fMRI data. And just to illustrate that, I'll show this example here. So we have a functional connectivity map, the correlation of the time series in the white dot location with every other time series in the brain, displayed on the brain. And this is what we get if we put a seed in the left inferior parietal cortex here. It kind of looks like a mess. Everything's correlated with everything. And that's because functional connectivity analyses, these correlational analyses, are very vulnerable to any non-random artifacts in the data. If we remove the artifacts from the subject moving their head, we start to get something a bit more specific here with functional networks starting to peek out, but it's still sort of a biased appearance here. There's more reds in the image than blues. If we remove the effects of the subject's respiration, we start to get a much more functionally specific network. We can see a default mode network here. And then if we remove random measurement noise without spatially or temporally smoothing the image, we get a nice map of the default mode here. So the point I'm trying to illustrate here is that most of the variation in fMRI data is not what you're interested in. So you really have to undertake these cleanup methods, remove the head motion, remove the respiration, remove the random noise. And that's really helped by having a fast TR of around a second. Most important for resting state analyses, but task fMRI analyses benefit too. You can use this to remove stimulus correlated artifacts that will affect your beta maps, and also the non-stimulus correlated artifacts and noise that affect your statistical significance. But even with the best denoising methods, so here I've talked about spatial ICA, temporal ICA, and Wishart filtering, the person can't be moving their head constantly throughout the entire fMRI scan. You need some good data for these things to work. So to get the high spatial, temporal, and angular resolution for fMRI and diffusion, it really helps to have simultaneous multi-slice imaging or multi-band, something that the HCP really popularized and people started using after the HCP had used it. And within reason, it's kind of like a rare free lunch in MRI. If you don't accelerate too much, you don't get that much signal loss. If you do it too much, you get issue with leakage between slices and G-factor effects. If you do this Caparina technique, though, instead of having the slices stacked exactly on top of each other, having them offset a little bit, it makes it easier to untangle them, and you can achieve greater acceleration. So if you combine in-plane and through-plane acceleration, it's sort of like a product. So let's say you have a in-plane acceleration of factor of 2, and through plane of 3, you get a 6-fold acceleration. But your total acceleration is going to be limited by the number of coil elements in your SAR. So if for a 32-channel coil that many people do brain imaging with, maybe a factor of 12 is about the absolute most you can do. But if clinical populations often require a 20-channel coil, heads are bigger in clinical populations, and there, a factor of 4 is maybe the max you can get. So optimizing an fMRI scan, you want to have a 3T magnet or higher field strength, 32-channel head coil or better. Spatial resolution, again, 2.4 isotropic is a nice place for fMRI. Spatial resolution, temporal resolution, around a second. Going slower is going to reduce your statistical sensitivity and your ability to remove artifacts, but going a lot faster actually has diminishing returns. So again, we've sort of backed off a little bit from what we've done in the HCP to a little bit less spatial resolution, a little bit less temporal resolution, but more SNR and a little bit more generalizable. So 2.4 isotropic spatial and TR of 1 second. And so we use a flip angle of 60 degrees at 3T because we have incomplete T1 recovery still. And we can achieve this with a SMS factor of around 6, or even actually on Siemens scanners, we can, if we're put our field of view of the fMRI very tightly around the brain, we can actually do it with 4, so we can even do it on the 20-channel coil. In-plane acceleration, if you're going to correct for distortions offline, you don't really need it, and it uses a lot of your SNR, but clinical populations where we don't have the ability to correct for distortion in the clinical workflows, we do use it just to reduce that. Make sure to optimize the echo spacing. That's the parameter that controls how much distortion is in your images, how much dropout is in your images, and it's very common to see clinical protocols where that number is not optimized, and so the images are much worse quality than they are. In terms of the contrast, you want an echo time near the T2 star of gray matter. That gives you the best bold contrast to noise, but then you have to balance that with the longer echo times giving you more signal loss. So people are usually using TE around 30 to 40 milliseconds. And multi-echo fMRI certainly has been pitched as having a lot of promise. I can tell you that I've played with it on several occasions and still have yet to have it beat optimized single echo fMRI, but I'll keep trying. It certainly theoretically has benefits. There's vendor intensity normalization, things like Siemens pre-scan normalize, or I'm forgetting what the GE and Philips terms for that are, but Basically, those are worth using. It actually reduces the impact of head motion on the brain. As the head is moving around in the receive field of the head coil, parts of the head are getting brighter and darker. And this vendor intensity normalization actually removes that, so you don't have to deal with it later. And then 7T, if you have access to it and your population is appropriate for it, can achieve higher spatial resolutions, 1.6 isotropic, the minimum thickness of the cortical ribbon with a TR of 1 second, but it's not a routine clinical approach. But what if you didn't follow all of these recommendations because you just showed up to this course and you have data that you want to process on the surface? What about that? Well, if all you have is a 1 millimeter isotropic T1 weighted image, that's okay. We can still do surface-based processing. The main limitations will be that the surface will be a little bit less accurate in thin, heavily myelinated cortex like the visual or metasensory cortex. Not having a T2 means that you're going to be more likely to include some blood vessels and dura within your cortical ribbon, because the T2, it's very easy to distinguish these, whereas on the T1, it's harder to distinguish. You can't make a myelin map, which is useful for localizing things and surface registration, but you can still do a folding registration. You can still make a surface mesh. So even if you have only a 1 millimeter T1 weighted image, you should still do surface-based analysis is the message here. What about fMRI resolution? What if it's worse than 2.6 millimeter isotropic? Well, it means you will have some more partial voluming than the higher resolution data across cortical folds, but you don't want to make that problem worse by smoothing the data in the volume, because that's just going to make the partial voluming, orders of magnitude worse than you're starting with. So you still want to get your data onto the surfaces. The toughest one is if you don't have a way of doing distortion correction, because there really isn't an accurate way to do it if you don't have a map of the magnetic field. You can use a boundary-based registration in FSL or FreeSurfer to optimally align your distorted image. Basically, what it'll do is it'll align the undistorted parts of the image. The distorted parts will still be misaligned. There are a variety of field mapless distortion correction algorithms out there, but there's not any that I would recommend at this point. And what you'd really want to see is that in data where you have a gold standard, where you have a map of the magnetic field, does this algorithm make the agreement between the fMRI and the structural better than not doing anything? And that's a bar that I haven't personally seen in one of these algorithms pass. It doesn't mean that it can't do it, but I'm just saying have some caution here. But my overall message is, even if you don't have the optimized MRI acquisition protocol, any neuroimaging data is going to benefit from surface-based analysis, and I'll talk a little bit about that in a second. So some key conceptual differences between volume-based and surface-based analyses. So in a volume-based analysis, EPI distortion may or may not be corrected, whereas it typically is in a surface-based analysis to ensure accurate volume-to-surface mapping. Typically, if people are often doing spatial smoothing, and they're doing it in the volume, so they're blurring the gray matter and the CSF and the white matter all together. They're blurring across cortical folds. On the surface, people often don't do smoothing at all because the statistics are already improved by mapping onto the cortical surface and averaging across the cortical ribbon. But if they do, you're not getting that partial voluming effect. You're not getting the blurring of the CSF and the white matter into the gray matter. And you're also not blurring across the cortical folds. Volume-based analyses, the cross-subject alignment is performed in the volume, whereas it's performed on the surface in a surface-based analysis, and I think we'll have more on that in a subsequent talk. People often localize their results in 3D standard space coordinates for volume-based analyses, but on the surface, people can do better than that. We can actually see if a particular area of activation overlaps with another cortical area and say that they're the same area or they're not the same area based on spatial overlap. And there are lots of variations in surface-based approaches, but these are kind of the key ones to keep in mind. So correct the distortion. If you smooth on the surface rather than the volume. Align across subjects on the surface rather than the volume, and then how you present the results downstream. And note that I haven't said, well, do your analysis in the volume and display it on a surface mesh, because that doesn't really gain any of these benefits, and that mapping to the surface mesh is likely not going to be particularly accurate. So you really, to do a surface-based analysis, you want to have done all 4 of these things, not just do this and then map it onto a surface mesh. There are a variety of software and surface-based pipelines for analysis, and this is not an exhaustive list. These were the things that I came up off the top of my head. FreeSurfer, Connectome Workbench, FSL has command line support for SIFTI and GIFTI in many cases. Civet is an example, so these are software packages. Brain Voyager has surface-based analysis, but you pay for it. Analysis pipelines, the HTTP pipelines support it natively, as does FreeSurfer. fMRI Prep, I believe, has some surface-based capabilities. So a little bit about how this works now. So FreeSurfer, which I'm most familiar with, is how we in the HCP generate a lot of our surfaces. So it's going to automatically segment brains, generate cortical surfaces, and align subjects on the surface. So basically, we take a T1 weighted image, and we get the white matter and the gray matter and other subcortical structures subdivided, and we can then use that to make a cortical surface. And here's an example cortical surface. So it's made up of these triangles. Where the triangles come together, we call those vertices, and that's where we tend to store the data on a surface-based analysis, and then there are these links between the vertices that form the triangles. And we can take a mesh like this and computationally inflate it to see the cortex inside of the folds. And then we can align across subjects in 2D on the surface using these folding patterns. So this does a much better job of aligning cortical areas than we can do in the volume. So we can take the same data. This is area MT. Here it is in the volume, and here it is on the surface. And we have the peak probability overlap here. So the spot in the brain where the probability map is highest, has the most overlap across subjects. We can see that's quite a bit higher on the surface than it is in the volume. Here it's in the maybe 25 to 30%, but we can get it up to around 60 to 70% with the folding-based surface registration. So when we undertook this effort to basically in the HCP to focus on surface-based analyses, we developed a new standard coordinate system and a set of analysis pipelines. So we have this SIFTI gray ordnance space that I want to tell you about. So that's made up of 2 surface meshes, the left cerebral cortex and the right cerebral cortex, each having around 30,000 vertices. And then we have subcortical gray matter voxels of around 30,000 voxels across 10 different structures, giving us around 90,000 gray ordnance. And so that's our 2 millimeter standard space for the SIFTI gray ordnance in the HCP, and probably most of this kind of data at this point is in this space. And it's also helpful, you know, we've pushed the spatial and temporal resolution of our fMRI data. That really increases the demands, but if we get rid of all the CSF and the white matter voxels, by just having our data in this gray ordnance space, it actually helps reduce the computational demands while improving the alignment of data across subjects. And so we developed analysis pipelines to get raw MRI data into gray ordnance. And we really try to minimize smoothing throughout those pipelines as much as possible while aligning within and across modalities and correcting for distortions. Doing even better at aligning functional networks and cortical areas. So many cortical areas and functional networks are actually not very well correlated with cortical folding patterns. So unfortunately, Emma couldn't be here with us today, but she developed a surface alignment algorithm that is capable of using more than just cortical folds. And I use this to generate what I've termed an aerial feature-based cortical alignment. So basically using things like resting state networks and myelin maps, task fMRI or topographic maps. And here I can illustrate what that does. So if we take our folding-based surface alignment as our baseline, and then it's the same data again, and we use resting state networks and myelin maps, our area MT is now even more precisely aligned with the aerial feature-based alignment than with the folding alignment. And it allows us to make cross-subject averages that are not blurry. We've got, these are two groups of 210 people listening to a story. And this is the task fMRI contrast here, and you can see that the maps look basically the same, and they show fine details. Like, this is the little hotspot here that I was pointing out in the first, one of the early slides, but we've got things like area 55B here and other fine details that are highly reproducible from one group of subjects to another. And the next major advance for surface-based alignment is actually likely to come from deep learning algorithms. So why are folding patterns not enough? Well, here's area 55B, and we can see that in one subject, it sits in a sulcus, in another subject, it sits on a gyrus. And so many cortical areas just aren't that correlated with folding patterns. In fact, all of these red and orange and green regions have relatively poor correlation between folds and where cortical areas or functional networks are. It's really only a few parts of the brain that have less variabilities, like the central sulcus or the insula around the medial wall here. And then, as I was mentioning earlier, smoothing in 3D, it may be widely practiced in brain imaging. It may make images more aesthetic and statistics go up, but it really makes localization quite a bit worse. So even if we have something that's well aligned in the volume, such as the somatosensory area 3B, the central sulcus is not so variable across people, so that's why it's reasonably well aligned. If we smooth that data, though, we can see it basically is much harder to figure out exactly where area 3B is. It gets a lot blurrier. We start out with an area that's not very well aligned. Smoothing doesn't make it better aligned, it just makes it harder to find. Another issue with smoothing is biases and localization. So if we focus here on the insular cortex, this is the probability of being in the gray matter ribbon. We can see as we increase the amount of smoothing, that probability starts to migrate towards the CSF here. So this is the CSF space here and the cortical gray matter and then white matter outside. And we can see the highest probability is now right in the middle of the sulcus if we use 8mm smoothing in the volume. So we really want to avoid this sort of thing. Smoothing in 2D on the surface is less harmful than 3D, but if you do it excessively, you can still make it harder to find things. So no smoothing, 4mm or 8mm, you can start to see some blurring here as well. Okay, so putting it all together and finishing up, a better HCP-style approach to brain imaging research. So we want to acquire high-quality, high-resolution multimodal data, avoid blurring brain imaging data, using 2D surfaces for the cortex, 3D volumes for subcortical nuclei, accurately align brain areas across people, use an accurate, functionally relevant map of the brain, and freely share brain imaging results and data in publicly available databases, such as the BALSA database, not just peak 3D coordinates. If we put it all together, say, what was in maybe 2012 the most common volume-based processing, aligning in the volume and also doing 8mm full f/2 maximum smoothing, you get something that looks like this for the area MT data. And then the recommended approach I presented to you here, where you align on the cortical surface, you don't smooth, and you use an aerial feature-based alignment, you can see really an enormous difference in your ability to do spatial localization. And I like to think of it like this is before adaptive optics came on the scene, that you just get a much sharper picture with a surface-based analysis than a volume-based analysis, like putting a telescope in space or having adaptive optics. But here, all you really have to do is change how you process the data. You don't have to spend billions of dollars on these things. So it's actually an easier change to get the benefits. And these benefits are basically universal here for typically used fMRI resolutions. So these lines here are different cortical areas and different resolutions. So 4mm data are in green, 2mm data are in blue, and 0.7 data, obviously not really a currently achievable fMRI resolution, but you can see that your ability to localize the signal of interest within a particular cortical area, not having it be off in a probability cloud, is always better for the surface-based analysis, even if you're talking about 4mm data. So any data that's out there is going to benefit from surface-based analysis. It's just a question of how much. And that biggest issue potentially is getting the distortion correction dealt with. but legacy data can be brought into SIFT. Okay, well, I think I'm probably out of time here, but if you want help with various things such as HTTP pipelines or HTTP data or surface-based analysis, our user group is a good place to ask questions. If you want to use the HTTP pipelines with containerized version, QDEX is our official container for the HTTP pipelines, and also there's lots of help on FSL and free surfer lists. And I think we'll move to the next talk.